All right. So binary numbers can represent decimal numbers, and decimal numbers can be converted to binary numbers, and you've practiced doing both. Super. So how does that help us understand what any of that has to do with what we actually do and see on a computer? Well, this lesson will help you understand what binary has to do with text. So in previous lessons, you really got to dive deep into binary. You found out that it is actually a base 2 number system, and that it's actually not all that different than a base 10 number system, just that the base is 2 and not 10. But every place holds its value based on 2 raised to some power, and the power starts at 0 and it increases by 1 as you move left in the place values. So you have a pretty good idea of what that is. But the question is, all right, now that you know all about binary, and you can even do some conversions, binary to decimal, decimal to binary, where is binary? We don't see it, so where does this come into play? It's everywhere. It's everything. It's images, it's sound, it's files like PDFs and Word documents, it's videos, it's the internet, the web pages. Everything that you want to do on the computer is powered by binary. In Unit 4, we're actually going to discuss pictures and audio and video in more detail because those do require some additional encoding using the binary system. But today, we're actually just going to talk about text because text is very straightforward in the way that it's encoded with binary. And so the question is, how can we possibly represent text with binary? Text is made up of what we call alphanumeric characters. Now, if you break that word down, we know that alpha comes from the alphabet, and that just means letters, all right? And then, of course, the second part of the word is numeric, which we know means numbers. So alphanumeric characters altogether, that just means all of the characters, like letters and symbols, special characters that we can type on the keyboard. And we're going to look at how that translates into binary. In the lesson, you have a really good video that explains this table right here. I would take a break right now and go watch that video and get an idea of what this table is all about, because I promise you it's not as complex as it looks at first. And then come on back and we'll pick up where he left off.
Look, everyone, it's the ASCII table. Man, that thing sure is iconic. It's more iconic than icons. So how's it work? Well, we know that the characters that we type on the keyboard and that show up on the screen are represented in the computer as bits. So we're going to take this ASCII table and basically convert bits into characters. Let's do this one right here. I'm going to split this up into two because the way this particular ASCII table is structured with the rows and columns, it's got 4 digits for rows and 4 digits for columns. And we're going to do this just like you do any other table where you have a row and a column. You find the point of intersection and read off the piece of information that we're looking for. So 0, 1, 0, 0. We're going to look over here and we see 0, 1, 0, 0. And then the second half is 0, 0, 0, 1, which we find here in the second column. So the point of intersection of those two is the capital letter A. Capital letter A corresponds to this. So when we type in an A, it's stored internally in the computer like this. One thing to point out here is that we're really only using, when we talk about ASCII, the top half of this table. There are 128 different characters, and this standard was formulated in the early 1960s. Obviously, since then, we need a lot more symbols than that, but the basic package is right here. It's got your capital letters or lowercase letters, numbers, very few symbols. And the strange guys up here, what are these? These are called control characters. They don't actually show up on the screen necessarily, but they have a function. So CR is carriage return. That's when you hit the enter key. BS would be backspace. SB would be system bell, which is, the little ding sound that the computer makes. All of these were originally included in the ASCII table like this. Now, we've got a bottom half here. This is the extended ASCII character set. It adds one more bit. We've gone from 7 bits to 8 bits. And you can see that bit over here, the leftmost column. If it's off, aka 0, we're on the standard ASCII table. If it's on, aka 1, we're on the extended ASCII table. Now, this isn't quite the same as far as standardization goes. In fact, you can tell what kind of computer I'm using by looking right here at 11110000. You see a little apple with the byte taken out. If I were running a Windows computer, the extended ASCII character set would be different. Some of it would be the same, but a lot of it would be different. I'm fairly certain this apple wouldn't be here. However, the standard ASCII character set would be the same, and there are other standards too, like Unicode, which extends the character set quite a bit, but this is the basic ASCII table.
All right, so now you know how the table is read, and you may have noticed little special things, like, for example, we've got the capital A right here, and we've got the lowercase a right here. And if we go and look, B and B are below each other, C and C, D and D, E and E, same with the letter U right here, uppercase and lowercase right there. So they're in the same column, which means that they actually have the exact same last 4 digits. All right. However, what's different between those two, for example, the capital A and the lowercase a, is if we look right here and compare, they both have zeros first, then they have ones, meaning 64. But then the 32's bit right here is on for the lowercase a, and it's not for the uppercase. And it's the exact same relationship. And you'll find that, for example, let's take it, so we know that if you're going to type a capital A on a keyboard, you have to hold Shift. Well, guess what that Shift does? It turns off the 32-bit, right? So when we're talking about shifted characters, how about, you know that, for example, to get the number sign, you have to hold Shift and type the letter 4, right? Well, look right here. Conveniently located is the number sign and the letter 4. And they're right there. And let's take a look at what the difference there is. Oh, look, it's only 1 bit difference in that first 4 digits. The 4 has a 1, where the shifted character has a 0 in the 32's place. So it's just kind of interesting to see the relationship between the keys on the keyboard and where they're placed on this table. And another thing that I want to talk about, if you have typed code before, and you're going to type code when we get to Unit 4, you'll notice, and we've talked a little bit about this as it has come up, when we're typing, for example, comparison statements or math symbols. We know that instead of being able to use symbols, I'm trying to scan and find one here, and my eyes aren't working too well for me. But, for example, right here we have the greater than or equal sign, right? And we said, well, we don't really do that. We only type a greater than followed by an equal sign, right, to compare. The reason for that is when we type code and when that code is compiled, which is pretty interesting. Remember that little software program that translates the code that we write in a high-level programming language down into binary, we have to stay up here. Our characters cannot be in this extended ASCII character set. It can only be the 7-bit character. If we start using these down here, our compiler gets really confused because it can't take this. It needs, if you've heard the term before, it's got to be plain text, right? Like a plain text editor. If you type code, you need to use a plain text editor. And that's because you have to stay up in this upper half of this table, right? Pretty interesting, because otherwise the encoding is different for the text and it messes up the compiler. Pretty cool how it's all coming together, right? Okay, but what I'll tell you is that you will probably not see the ASCII table that way on the exam. You will probably see the ASCII table something more like this, where it's not exactly a matrix, multi-row and column grid, where it's just showing actually decimal values rather than binary values. All right, so this is more likely something that you would see. It might not be the capitals, it might be the lowercase or whatever. But in any case, what they would do is they would provide you with probably the decimal equivalent to that ASCII character. For example, A is 65, right? And they would ask you, okay, can you put that into binary? What is the binary equivalent for the letter A or for the letter G or something like that, right? Or they may give you the binary number and say which of these letters in this table is most likely encoded with this binary sequence or something like that. All right, so let's talk just a little bit about that. Let's just look at letter A, capital letter A, because that's an easy one to look at. That's 65. So the question is, why is it 65? Well, if we go and we translate, and here's what I recommend to my students that they do. I recommend that they make something like this. 1, 2, 3, 4, 5, 6, 7, 8. And then that they do something like this. 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. And if you want to even go a step further, you could go in and you could, I'm just going to write on top here now, you could do your 1, 2, 4, 8, 16, 32, 64, 128. You can even do that. You can do this in the workspace that you have in your folder. Anyway, so 64. Oh, I just gave my thinking away. So the number 65, the first thing we want to do is figure out, okay, well, how many groups of 128 can I make out of 65? Well, clearly the answer to that is 0. Well, how many groups of 64 can I make? Well, the answer is 1. I can make one group of 64. And when I do, and I take that group of 64 away, I'm left with 1, which means that I get 0, 0, 0 here, 0 here, 0 here, and here is my one little leftover. All right, so there is my binary sequence for the letter A. Okay, so remember that, 0, 1, and then all zeros until the last one. All right, when I click back over here, well, let's remember that. Remember, I told you it was 0, 1, 0, 0, so the 64's place had a 1, everything else was zeros, and then everything else was zeros until the last one. So there we go, 0, 1, 0, 0, 0, 0, 0, 1, right? So then there it is, right there, sitting at 65. Okay, so that is 65 right there. All right, so this table, I think, is more comprehensive in terms of its ability to explain to you why the different characters on the keyboard have the particular binary sequence that they do, but just remember that you're more likely to see something like this on the exam. Okay, and just so that you understand, it's important that you understand why these particular decimal numbers are associated with these particular ASCII characters. Just to kind of bring all of this to a close, remember, one aspect of computational thinking is abstraction, and that is a big aspect of computational thinking. It's really important. Ultimately, computers literally need to be told which little circuits to turn on and off. They don't understand language. They don't understand symbols. The letters are symbols. They don't understand words or anything like that. They don't know the difference between capital letter A and lowercase letter a. The only difference they know is the difference in ons and offs of the circuits. So this abstraction where we can actually envision these letters as binary sequences, as decimal numbers, remember that is important to the ability to map these values to symbols, so that we can kind of create the illusion that computers can understand language. All right, but ultimately this is an abstraction that's more for us. The computer really doesn't understand. Alphanumeric characters in binary can potentially yield some problems. There can be errors. The errors might be in the process of actually sending this information over the internet, in the process of encoding something into a different format. Who knows what the process is, but somewhere when we process data, there's always a chance that there can be an error. So you can see on the screen that the letter G and the letter W, these are lowercase letters, non-shifted characters. The only difference is right over here, this bit right here. So we have 0, 1, 1, 0, and the letter W is 0, 1, 1, 1. Okay, so there's this one bit of difference between the letter G and the letter W. And that's just one teeny tiny little switch that could accidentally get tripped on rather than off. And imagine that, like, this cake is really wood. What? Wood? The cake is wood? The computer doesn't know that that doesn't make sense and would not have a problem displaying a sentence such as that. Not good. See what I did there? So anyways, it can really change the meaning of the sentence, but the computer doesn't know that. All right, so it's noise. So noise is irrelevant or meaningless or mistaken data that has found its way into otherwise meaningful code. All right, and there are different types of algorithms that will check for errors before data is processed. Like, for example, before data is transmitted or before data is encoded into a different format. There are algorithms that will correct, well, that first will detect the errors and then potentially correct them as well. And that's why typically we don't see errors like this. So otherwise, as a result of noise, instead of what you were expecting, you could end up breaking your teeth on some wooden cake or something like that. Or even worse, have a message that can't come through because of errors, and then you end up with the blue screen of death or the spinning wheel of death, neither of which are good things. We don't like those. So we are grateful to those algorithms that are able to check for those errors, because you can see how easy it is for them to happen. It is important to remember that English is not the only language spoken anywhere. English, with its 26 symbols, yes, we've got special characters and caps and non-caps and all of that kind of stuff, but other languages have plenty of other types of characters that we would need to allow for. And remember that ASCII was, the A standing for American, right? American Standard Code for Information of Interchange. ASCII didn't take into account the needs of other languages in terms of being able to type them. For example, in Spanish, we have this special letter, ñ, and it is very different than n, right? And we really want to be able to type correctly when we're typing in Spanish. And so the ASCII system didn't have room to allow for this particular character right here, okay, which is problematic. So it's a limited set of symbols, again, only up to 7 bits, so only up to 128 different values. Obviously, something had to change as computers evolved. We needed to include other languages. Right now, the answer to this is Unicode. All right, and this is a binary encoding system that can represent way more of the world's text than ASCII can. So the difference is that while the ASCII table includes 2 to the 7th values, or 128 different values, Unicode can represent 2 to the 16th, okay? 2 to the 16th power. All right, so look how quickly that value increased, or the amount of different characters that can be represented increased. Okay, that's a huge difference. And that allows for Asian characters, Spanish characters, French characters with the different accents, and things like that. And we needed to be able to represent those. And so right now, the Unicode system allows us to do that. All right, so here's an example. The letter capital U, shifted U, can be represented in ASCII. We have, again, this 32-bit here is on, and I would guess that the lowercase u would just be different by 1 bit. But anyways, we're talking about the capital U. The capital U, here it is, right here. That's exactly the same number. The only difference between how this looks in ASCII and how it looks in Unicode is all these leading zeros, right? And we said that the leading zeros don't change the value of the number. This is a small number right here. It's just that we put a whole bunch of zeros in the front of it to hold the places, to show that those places actually could be occupied by a 1 if we wanted. So extra zeros at the beginning are just padding the Unicode equivalent, right? Just to show that really, yes, we could have filled up those zeros with 1s up to 2 to the 16th places. Okay, so 8 additional places. So how does this all translate to typing on a keyboard? Because if you've ever tried to type, for example, in Spanish or in French, you know that those characters still don't show up on our keyboards. Now, if you're on a touch screen, like on a phone, you can kind of long press on the number that has it or the key that has it, and you know that you can just click it. However, on a standard keyboard, in other words, on an ASCII keyboard, that is not possible. All right, so before Unicode, we could not type jalapeños, right? We couldn't type it because, like I said, we didn't have the ñ. We couldn't type that. So now we can actually type the word as it's supposed to be written. Before, we would just have to leave the tilde off and it would just say jalapenos. So the question is, how do we get that then? Because there is no ñ key on the keyboard. All right, so even with the keyboards that are primarily found in the US, we can actually use, type, and encode in many other languages. You just need to know the appropriate keyboard sequences. For example, if I wanted to type an accented O on my Mac keyboard, all I would have to do is type Option E. I would hold down Option and E, and then I would release them, and then I would type my O, and I would have an accented O. All right, so that's all that you need to know. And there are resources linked at the bottom of a lesson so that you can actually go in and check out, well, what if I want to type this or that? And really, anytime you want to do something like that, you just need to look up, how do I type accented O in Spanish or something like that. And there are more language-specific keyboards linked at the bottom of the lesson as well. All right, so this is a pretty good introduction to how we represent text to the computer when the computer only speaks binary.